So in my next section, I'm just going to explain about finite element modeling and elements and its degrees of freedom. So finite element modeling is nothing but meshing. How you are going to discretize your physical entity into the finite element model, and what are the types of elements available, and each element will have its own degrees of freedom. So we are going to see about this. So first, I just want to explain about what are the different types of elements available in the FEA. So you can see that 1D elements, 1D elements, 2D elements, and 3D elements. So in the, for example of 1D elements, you can model bars, truss, beams, tubes. So if your application depends on beams, pipes, you can model it in the 1D elements itself. And for 2D elements, there are two different types of 2D elements. One is your trias and quads. Trias is nothing but triangular element. Quad is nothing but quadrilateral elements. And 2D elements, or example, you can say shell elements. So if you're going to model any your aerospace or any ship pulse or your length with thickness ratio is very less, you have to go for the shell modeling. So for those type of modeling, finite element modeling, you will use the 2D elements. And for 3D, there are two types of elements. One is tetra elements and hexadragon elements. Tetra element is nothing but 4-node elements. It will be a triangular pyramid-like element, and hexadragon is a cube. It's like a brick element. It has 6 degrees of freedom. So if you take a 1D element, you will have 2 nodes for each element. And if you have 2D element, there are 2 types of 2D element, trias and quads. For trias, you will have 3 nodes, and for quad, you will have 4 nodes. And if you take a 3D element, for tetrahedral element, you will have 4 plus 1, 4 elements, okay? And for hexaedric element, you will have 6 elements. Hello? Can you hear me?
Yes, Arjun. Arjun has a question for you.
Hello, sir.
Yes.
I just wanted to ask, like in the 2D element, you have shown the model of the aircraft, right?
Yes.
And told that it's a shell element, that's why it's 2D. And how is that any difference from the piston, sir? Even that's kind of a shell model itself, right? Like, I mean, the way
that what I said, that you have to selection of elements is based on your application and your thickness. Okay, if your thickness is more, you can't go for the shell element. Length waist thickness ratio. Yes, you have to select the element based on the length waist thickness ratio.
Okay, so the similar 2D element can be used for that piston also, like while modeling?
No, you can't use the shell element for piston. If you do that, you can get the results, but your result will not be accurate, because your piston will have a lot of profiles in it. Okay, so you can't match those profiles. If you want to match it, you have to mesh it with the higher elements. Again, your computational time will go high, but your accuracy also not much better.
Oh, okay, sir.
You can't actually you can't cover all the geometry using shell elements. So as we seen in our example 2, so how much that covering that area, how much you are covered now, then only your accuracy is increased. So you have to cover your shape initially. So how much the possibility of covering the shape will give much better accuracy. Then only your results are also accurate.
Okay, so can we use those 3D elements for that airplane one?
Sorry?
Can we use those 3D elements for the aircraft model? Like,
yes,
can
yes, it's very good question. I'm just going to answer it in my next thing. Before that, I will just answer this question. Your good name, Arjun, right?
Yeah.
Yes, Arjun. I will just answer your question in the next slide. Why we can't model the aircraft in 3D elements? Huh?
Yeah, sure, sir. Okay, thanks.
So, okay. Next one is element convergence.
Ashwin, we have a question from Swapnil.
Yes.
Swapnil?
So I got my answer.
Yes, okay, thank you. So next to what I am going to tell is element convergency test. What is this? So you can ask one question to me, sir. So you're saying that if I mesh it finely, or if my number of elements is high, then my accuracy is high. Then what is the elements size I should mesh my product? You can ask this question to me. So for that, what we have to do is you have to perform the element convergency test. You can perform the analysis by increasing your number of elements, and you can check for the displacement. So what happened is at particular time your model will get stagnant. So you can see in the graph, if you are reducing your element, and if you are performing your displacement is actually the true displacement of the structure is the top one, but your results is coming down somewhere if you have a very poor model. But at particular time, what happens if you keep on increasing your elements? At particular time, your model will have the stagnant results. That point we called as it's a correct element size to perform the analysis. So this we called as element convergency test. Any question in this? You should not mesh finely, or you should not mesh coarsely. Your model should have optimum element size that will have that will reduce your computation time. So to find out which is a better element size for meshing, so to find out the element size, what is a perfect element size, we have to perform this element convergency test. Any questions on it?
No, sir, you're good to go.
Yeah. Okay, I'm just moving.
Ashwin, one thing. Abhishek was asking,
Yes.
solid element is having more volume compared to shell elements. Is that the reason for using 3D element?
Can you repeat that question once again?
Solid element is having more volume compared to shell elements. Is that the reason for using the 3D element?
No. The answer for your question is next slide.
Okay.
So the another criteria of selecting elements is your degrees of freedom. Each element has its own degrees of freedom. For example, if you take a 1D element, you will have a lot of elements in it. 2D element, in 1D element itself, you have a lot of elements like truss element, beam element, pipe element. If I take a trussed element, you will have only 2 degrees of freedom, ux and uy. Anyone can say what is the degrees of freedom a object in space?
6.
What are they?
3 translation, 3 rotation.
Okay.
Yes.
Very good. So if
Thank
you
you,
take a one, if you take any one element, 1D element, you will have only 2 degrees of freedom. That is ux and uy. Translation in x and translation in y. So you will not have translation in z and all 3 rotation. So you will have only 2 degrees of freedom for the 1D element. And if you take a beam element, you will have ux, uy, and rotation along z axis. The rotation along z will enable in your degrees of freedom to enable your bending properties, bending and shearing properties. That's why for truss problem, for any bridges, steel bridges or anything, it will have only the axial displacement. It will not have any bending or something. So that kind of problem, we use a trussed element. And if you want to know about the bending property of the truss or bending property of your structure, you have to go for the beam element. Beam element will have 3 degrees of freedom. Clear? And your pipe element will have all 6 of freedom. So if you take a 1D element, there are 3 different kind of elements. One is truss element, beam element, and your pipe element. Truss element will have ux and uy, only 2 degrees of freedom. Beam element will have 3 degrees of freedom, ux, uy, and rotation along z. This rotation along z is used to capture the bending capabilities of the beam or column. And pipe element will have all 6 degrees of freedom. You can find out all axial displacement, bending, shear, stresses, everything in the pipe element. Okay, and next 2D element will have again 2D element will have, there are a lot of 2D elements. One is plane stress element, plane strain element, shell elements. Plane stress element and plane strain element will have only 2 degrees of freedom, ux and uy. It will not have other degrees of freedom. And for shell element, all 6 degrees of freedom is available. So you can also study about the bending in the shell element, not on plane strain and plane stress elements. And if you take 3D element have 3 degrees of freedom, ux, uy, uz, and rotation is taken care in the element shape itself. Shape function of the system will take care of all the rotation degrees of freedom. So let me explain once again. For 1D element, you have 3 types of element. One is for truss element, you have only ux, uy. For beam element, you have ux, uy, and rotation along z. And for pipe element, you have all 6 degrees of freedom. So if you come for a 2D element, you have 2 types of problem. One is plane stress strain problem, plane stress strain element, and shell element. Plane stress strain element will have only ux and uy, and shell element will have all 6 degrees of freedom. So 3D, if you come for a 3D element, you have 3 degrees of freedom, ux, uy, uz, and other rotation 3 degrees of freedom taken care by the shape function of its own element itself. Clear? Now I am coming to the computation part. Okay, so Arjun has asked one good question: why we should not mesh the aircraft with solid elements? The answer for that question is for finding the computation of the analysis, there is a formula: number of elements into degrees of freedom. Number of elements into degrees of freedom. Okay, if I'm taking the aircraft, I'm going to use a shell element. Okay, then I'm going to model with 2D element. So I will have I can for example, I'm having 1 lakh elements for modeling the aircraft. 1 lakh element into 2 degrees of freedom. Okay, or 6 degrees of freedom. That will give you the computation time. If I model in the solid thing, so number of node will increase. Okay, into degrees of freedom. So your computation time will be more when you model on the solid using solid element. So only we are not modeling in the solid elements. Clear, Arjun? You have any questions?
No, sir.
So what you mean by 3 degree of freedom including shape function in case of 3D element?
Shape function is nothing but that rotation on x, y, z now, that will taken care by the nodes itself. Node, if you apply a force on the node itself, the node will take care all the rotational degrees of freedom. So for this you have to study about what is shape function in FEA. If you take theory book in FEA, there is a subject called subject is called shape function. You have to study about the shape function. Then you come to know about it.
Hello, sir.
Yes.
Yeah. When we do kinematic simulations in CATIA, we give that for the amount of inputs we give based on the how many outputs the motions we get. We define the degrees of freedom over there. Is it the similar concept over here also? Like, I mean, the way we see
that is totally different, and this is totally different.
Okay.
This degrees of freedom is differently different from that.
Oh, okay, sir.
That you will check the degrees of freedom to reduce the redundancy error, right? Here is this degrees of freedom to calculate the computational time.
Oh, okay, sir.
That is totally different from this. So shall I move to next one?
Yeah, sure.